Okay, so here we go. Last time we were talking about functions of several variables, kind of getting started with what is a multivariable function and actually rewinding a bit to what is a function. And again, this very important distinction that a function is a trio. It is these three things. It's not just a formula, common misconception, right? And then a bunch of details and terminology, etc. But what we found is that it's very important to see these distinctions because while these two functions look the same, I mean, come on, they're both x squared, right? Who cares, right? One of these is invertible. And, one of these is invertible, and the other one is not invertible, right? So important distinction. You can't just go around saying, oh, the inverse function, if you don't know the inverse exists, and you can't know the inverse exists unless and until you've been precise about what are the domain and the target. Okay, so picking up from here, just another example. People talk about arcsine all the time, right? Okay, fine. But if that's going to be the inverse of the sine function, notice that sine, the typical sine function, defined on all real values, and target being the real values, right? Not invertible. You have to restrict the domain and the target for this to be invertible. So specifically, notice I've restricted the domain to being just these values of theta, and then I've restricted the target to being just these output values, right? And now notice for every input value, there is exactly one output value, and furthermore, for every output value, there is exactly one corresponding input value. Right? So as I've got it defined here, let's see here. This trio, this specific domain, this specific target, that formula, sine, is invertible. Everybody on board? Okay. All right. Quick reminder while we're here, I think it's worth pointing out, people do have a strong attachment to graphs. And that's okay in a sense. I'm going to say more about that later today. Actually, it's not as okay as you might think. But just also make sure to remember as well that there is a different way of thinking about sine and cosine, right? But let's focus on sine in particular. And what's the relationship between angles and values? And rather than thinking of it in the graph context, nice though that is, there is something to be said for thinking of it in the unit circle context, where the angles from minus pi over 2 to pi over 2 are those angles, and then the values of sine from negative 1 to 1 are these values, and so then the relationship between them is like this. So for my own money, the way I think about, how do you remember which way does arcsine go? Which values does arcsine take? I don't think about the graph of the sine wave and which part of the graph fits better, right? I think about this picture because it's just so immediately easy to see that for every point on this green semicircle, right, there is exactly one corresponding value on the y-axis and vice versa, right? Just an easy sort of one-to-one pairing, and thus easy to see that defined like this, in other words like this, that this, what I'm calling the invertible sine function, is invertible. Okay. Is everybody happy? Okay. A little bit of terminology here, and I know, time being as valuable as it is, I'm going to be pretty quick with this. But we'll talk about different kinds of functions. And notice that whether the function is real valued or vector valued, it's a reference to the values. It's a reference to what comes out. Is it multiple different values, namely a vector of values that comes out, in which case we have a vector valued function? Or might it be just a single number, in which case m equals 1? That single number is a real number, and so thus the term real valued. Analogously, we use the term single variable and multivariable to refer to how many inputs, right? So an important distinction there. But these terms are going to get used a lot. And as a nice example, let's talk about vector-valued multivariable functions. Right? So what is a vector-valued multivariable function? Okay, well, vector-valued means that the outputs are vectors. And here is a vector of outputs in this, what I call the weather function. Anyway, there you go. So vector valued because there's multiple outputs. Multivariable because there are multiple inputs. Right? And this is a reasonable function to talk about because if you want to talk about the weather, well, we can't do that until you tell me where you are on the surface of the Earth. And I suppose I should, just to be clear, I should be precise. Are you actually on the surface, or maybe you're up at some altitude, right above the surface of the Earth, whatever. And by the way, when? Are we talking about now, or are we talking about last Tuesday, right? So weather required, you can't even talk about weather until you know these, what I'm going to call inputs to this function. And then once those inputs are given, then you can talk about the weather. You know, what's the temperature, the barometric pressure, blah, blah, blah. Right, other aspects of weather you could discuss. So this is an example. I like this example because it shows the suggestion I've made here that these sophisticated mathematical constructions, vector-valued multivariable functions, sounds pretty abstract and obscure, and it's not. It's a mathematical representation of the most trivial of water cooler conversations, right? Talking about the weather, right? You know, conversation's dead when you're talking about the weather, right? So they're everywhere, vector-valued multivariable functions. And I've given you all the speech already about how multivariable calculus is the calculus of the real world. So another example of that. Okay. So now let's talk about how to draw pictures of functions. And this is a more complicated topic than you might think. There are some delicate subtleties in this, so be on the lookout. I am going to start with something that hopefully is familiar, that is the idea of the graph of a function. And here's our old familiar example, single variable graph. Right? But let me write down a general discussion. The big idea of a graph is that you take the inputs to a function and the outputs from a function, and you kind of smash them together to make a great big ordered n plus m tuple, right? Of coordinates. So input coordinates and output coordinates, both in the same point. And the collection of all of these is called the graph of that function. All right? This is familiar, perhaps. Let's take a look at our primary sort of first example. We write down the equation. Here we go. Here we have a function. Notice single variable, real valued function, right? Math219 kind of function. And let's write down this equation, inputs and outputs, and notice that if we put the input and the output together into the same point and look at the collection of all such points, we get the graph. The familiar construction from Calc 1, even long before Calc 1. Is that cool? Is everybody happy? Yep. Okay. So now, let me give you a different position on this, kind of a different take. And that is, let's ask the question, where did this equation come from? I'm going to point out there is something a little bit arbitrary about this equation. We were not really given that equation. We were given a real valued single variable function called f. Arguably, I need a dummy variable with which to write down the formula for f, right? So maybe x we'll say is arbitrary, though it may be kind of a given in talking about a function. But what comes out of the function, f of x, has a name already. It's f of x. We are choosing, as part of this graph construction, to take that output, f of x, and we are choosing to say, I'm going to call that another variable. Now, I'm going to point out, that's kind of weird. This is, as previously discussed, a single variable function. I'm bringing up a second variable. That's on me. That's a choice. We do not have to do that. This is arbitrary part of a choice. Right? So, anyway, I just want to point out that is not a given and it's not required. That's a choice. Now, it's a good choice. Right? It's a well-informed choice that leads to a nice tool, way to visualize functions. But it is a choice. Okay, so one way, 2 seconds. One way to think about a graph is that a graph is what you get when you set the outputs from a function equal to a new, previously unused variable. And everything, in some sense, after that, everything is a given, because after all, once you write down that equation, you have an equation of two variables. It's already long since established what we mean by drawing the solutions to an equation. Let's just plot all the points where that equation actually works, which is, in fact, the same thing. Okay, yes?
Yeah, so just to check my understanding, I feel like y is kind of decided by x, right? Since y equals fx.
The value of y is, according to my choice, I'm choosing to let y be f of x. Then yes, the value of y is determined by x.
I mean that in that case, if we can express y using x, isn't that still only one variable x?
Oh, yeah. I mean, certainly in this sense, this is still a single variable function. Yeah, absolutely. Okay. I'm just saying that not only is this a single variable function, but before I chose to give a name to the output value, there was no second variable in the first place. Right? There was only a single variable. Exactly your point. Right? So it's a choice to introduce a second variable, as I've done here, into the discussion, to allow me to draw this picture. Yeah. Okay. All right. No problem. So again, two different ways to think about a graph. In practice, most of the time, I tend to like this one, where a graph is what you get when you choose to set the output values equal to a new variable. Everything else kind of follows from that. All right. Now let's see a second example here, and I'm going to leave the first example up. What if we have a function of two variables? Right? This is now a multivariable function because there's two inputs. Okay, well, so following our rule from above, a graph is what we get when we set the value of the function equal to a new variable. Now, I've written, you'll notice I've written the function itself in terms of these variables x and y, so I can't set f equal to either x or y. Those are already spoken for. Those are input variables, right? So I'm choosing to set the value of the function equal to, I guess, z. It doesn't really matter. It's an arbitrary choice as well, but, why not? And so having chosen to let the output values equal to this new variable z, now I get an equation. And I can plot that equation, and I'm going to get a surface. And now, how do I know this is what the surface looks like? Let me return to our original point of view on what a graph is, and that is that a point on the graph, I suppose I could write like this. The inputs are the first coordinates of a point on the graph, and then the output, there's only one of them in this case, the output is the next set of coordinates, well, in this case, the last coordinate, singular, of these points. Said differently, for every input value that you kind of, in some sense, view as being from the domain, of the function, which you kind of visualize as being sort of down there, the xy plane, because x and y are my input variables. For every such input, I get an output, namely a value of z, which is an instruction of how far to go up, right, from that given input point. And the result then is this point. So you can view, why do we get a surface here? Well, it's because for every point in the xy plane, the formula is giving us an instruction of how much to lift it up. And so geometric appeal, if I start with a two-dimensional surface, namely a plane, and if every point gets kind of pushed upward by some amount, the result is going to be a two-dimensional surface. Okay. Is everybody on board? Let me go ahead and like that. There we go. Okay. All right. So seems like a natural extension of what we did in single variable context. By the way, I want to recognize I like graphs. You're going to suspect otherwise after I talk about them for a little while. But I really do. I like graphs. And let's talk for a moment about how great graphs are in a single variable context. We draw graphs of single variable functions. They are in a two-dimensional world. I have two-dimensional paper. It's perfect. The graph itself is a one-dimensional curve. That's what pencils do. It's awesome, right? It's the perfect kind of picture to need to draw to represent a single variable function. You couldn't ask for any happier conclusion. A little bit weirder when you get to this context here, a function of two variables. Now I gotta pretend that I can draw three-dimensionally, and we get this diagonal line, the x-axis drawn diagonally to create the illusion that it's coming out of the screen. But you really have to work with me on that, right? You have to want to believe, right, for this to work. And then likewise, notice I need to draw a two-dimensional thing, and notice I didn't. I drew a kind of an outline, right, that makes you kind of, again, the cooperative viewer might sort of visualize, okay, I think I see what's going on here. But notice where I have highlighted in yellow here, blank page. I didn't actually draw anything there. That's an illusion, right? So already in the most simple of multivariable cases, the graph construction is a little hard to draw. It's a little suboptimal. And now let's look at the next example. Let's talk about a function of now three variables. Like so. Right? Function of three variables. We'll follow the rule where we'll take the input variables. Right? We'll put them first. X, Y, and Z are my three input variables. I set the value of the function equal to a new variable. That's the output variable. In this case, I'm calling it W. Again, doesn't matter. Whatever. And we put all this onto the same, coordinates of the same point. And notice that this is a point that lives in R4. And I can't even fake that. Right? We cannot draw in R4. It reads it plausibly, right? Graphs are a problem. They are something that we're extremely accustomed to. So accustomed to graphs, we almost kind of take it for granted that that's what a function is, right? How often is it that you've looked at a curve like this and referred to it as a function? We call it a function because that's overwhelmingly the most common and best way to draw such a function. But we cannot do that in this. Just the next simplest possible case of a multivariable function. The graph is off the table. Can't even pretend to draw it as four-dimensional. Everybody see the problem? So two things on here. So as I've got drawn here, please do not conflate a graph with the function itself. A function is a thing We can write down all kinds of functions of all kinds of, several variables in, possibly several variables out. That's no problem. The graph is a picture arbitrarily defined by certain arbitrary choices and rules that in most cases we can't even draw. Right? So very important not to view these as being the same thing, and very important to accept that there are going to be other ways that we're going to draw pictures. That we really need these other ways to draw pictures of functions, because the graph is not going to help us most of the time. Does that make sense to everybody? All right. Okay. So let's talk about these other ways to draw pictures. I like to call this one the literal picture. I have to admit, I don't recall ever seeing an actual name for this. I think the literal picture is a pretty reasonable way to describe this, because if you have a multivariable function, keep in mind the multivariable function has three parts. There's the domain, the world that the inputs come from, and check it out, I am literally drawing that domain, R3, right? I've drawn a little, there it is, that's R3. And then let's see, the next part of a function is the target. Okay, all right, I guess I'll draw that target, R1, the real number line. There it is, literally, right? And then the third part of a function is the rule of assignment, the thing that takes the inputs and gives the outputs. The formula in most cases, right? And, okay, well, I'm just going to draw an arrow representing the action of, when you have an input point like this, it's going to get sent by the function over and land on as an output value somewhere there in the target. So this is, pretty literally just drawing a picture of the function as it is fundamentally defined. Does that make sense to everybody? Now, let's quibble about why we don't like this. There's some obvious things not to like about this. It is pretty unhelpful seeming, right? I mean, we're comparing, we're thinking in our minds about, does this do the job that this picture here did, right? This picture here, look, I see a shape. And we've studied single variable calculus. We know that certain geometric aspects of this shape, like the slope or the curvature, right, the concavity, we know that geometric aspects of this picture tell us algebraic information about the function, the derivative, the second derivative, algebraically defined things. So what a fantastic picture. I see, in some sense, I see the whole function. I don't see the whole function here. I see what the function has done to a single point A, and I see its image, a single output value f of A. And that is it. So very disappointing, right? But before you reject this, let me point out, it is a picture. You got to give me that. This is a picture, and it's a picture of a function with three variables. So if you say, I like graphs better, are you sure about that? Because when we tried to use graphs on a function of three variables, crashed and burned. So no picture at all versus disappointing picture, you got to go with the disappointing picture. Does that make sense? Okay. The other pitch I'm going to make for this is there actually are some nice things that we can do on this picture. Let me go back to the single variable again. So looking at this picture right here, there are certain things that we talk about with respect to this picture, such as at a given point, what's the derivative? How do I think about the derivative? And we talk about the tangent line, and we could talk rise over run and stuff like that. But notice, as we're discussing the derivative, I don't need any of this, and I don't need any of this. I really, if I'm interested in the derivative, all I need is to know what the function is doing at and very near one point, right? So I can actually kind of do that in this context. So let's think about this point right here, right, A. and it's got its output value over here, f of a. And here's a reasonable take on how to give some representation of something that will be kind of familiar, perhaps. We'll say more words about this later, but something that's vaguely derivative-like. And that is, if I am at this point, and if I start moving with some velocity in the domain, I mean, that's plausible, right? I could be here, I could be moving. Then, reasonable question, I'm going to different points in the domain. The value of the function, therefore, is going to change. And as I move thusly in the domain, I will have some corresponding movement in the target. And so a reasonable thing to ask is, okay, given if I'm at a certain point and moving with some velocity, how is the output value going to be changing? And notice, now I haven't answered that question, but I've drawn a picture of that question. This picture serves actually just fine for this purpose of asking the question of how does motion in the domain relate to motion of the outputs in the target. Everybody happy? So again, in a difficult situation where we don't really have any other options, this is a pretty decent picture of sorts. And I'm a big fan, and we're going to be drawing pictures like this a lot in this class. Okay, moving along. Level sets. Level sets are pre-images. Recall we talked about the idea of a pre-image last time, I'm pretty sure it was. When you have an input, what comes out as a result is the pre-image. Turning the other way, if you have an output, you can ask what are the corresponding inputs that landed on it. So notice that's exactly what's being said here in this definition. Let's see here, definition here of a pre-image of a level set, which again, as I claimed, is a pre-image. A level set is the set of wrong color. Sorry. Set of inputs to the function. Specifically, if you indicate a particular output value, right? If you give me a particular output value B, for a given output value B, you can ask what are the inputs that land on that given output value B. So this is literally a pre-image. Now, just for sort of getting the feel of things, let's do an example here. And here we go. Let's look at, I'm sorry, I got a little ahead of myself. One other little quick thing I wanted to mention. Again, given this idea that an input has an output that we call an image, an output gives rise to inputs that make that image, right? But there is a sort of a moving backwards through the function aspect of this idea of talking about pre-images, and so thus this notation, F inverse, right? We say F inverse of a given output because given the output, we're asking questions about what are the corresponding inputs. It's like we're going backwards through the function in some sense. Is that okay? Everybody okay? Yeah. Mm-hmm.
Can level sets only be used for invertible functions?
No, that's a great question. I hear you. When I write F inverse, it really makes it look like I'm talking about the inverse function. And really, that's true. I mean, we really should, in some sense, reserve this for where this has always been used to represent an inverse function, and that makes it seem like it should have to be invertible. But we need to talk about these pre-images not only sometimes for non-invertible functions, but usually for non-invertible functions. So this is yet another example of an abuse of notation, right? But it's extremely common. And so this is just another one of these things where you just kind of have to get used to the idea that, they write, this is suggestive of something that's just not the case. So F does not have to be invertible, and this F inverse does not mean the inverse function in this context. Yeah, great question. Thank you for that. Okay. Let's see an example. By the way, is it just me or is it really warm in here? Could you do me a favor? Just flip that switch right there. That'll turn on the air conditioning. Just there you go. Okay, that'll help. Okay, so here's a multivariable function. Right? Notice 2 input variables. And let's see here. Let's talk about some level sets. Keep in mind, the idea of a level set is for a given output value. We'll start with the output value being 1. For a given output value, I want to know what are the corresponding inputs. Right? What inputs in the domain, what points in the xy plane, when you plug them into F, will land on this prescribed output value 1. Right? Well, the way we're going to do that is we're going to literally write down, well, I want the output value to be 1. I want that to be the output value of this function. So I'm literally asking the question, what are the x's and y's for which the output value of the function is this prescribed output value 1. And notice what that means is I've written down an equation. Right here, let me use a better color choice here. Let me dark blue. I've written down an equation, x squared plus y squared equals 1. So algebraically, the question of what is this pre-image, what is this level set, is, well, what is the set of solutions to this equation, x squared plus y squared equals 1? And that's old news, right? We all remember this from high school algebra. That's a circle centered at the origin. So that then is f inverse of 1, the pre-image, the level set for 1. Is everybody on board? And you can do the same thing for other values. So, for example, let's take the output value 2. Well, the output value 2, okay, I want to know when is the function equal to this output value 2. That will be f inverse of 2. And notice this, again, is an equation. This is an equation representing this level set, f inverse of 2. And again, this equation familiar. Again, it's a circle. And again, I can just write it down, and it's a circle like that. Yep.
So the answer is the circle?
Yeah, yeah.
How would we format the answer?
So each one of these circles is a level set of the function. Yeah. So now that does bring me to another good point, which is that when we use level sets to represent functions, typically we will draw more than one, because it's not like there's anything about these specific output values that is all we care about, right? Very often we're interested in the whole function. And so we have to look at a lot of different output values and thus draw a lot of, well, circles in this case, and we'll have, therefore, a lot of level sets. Yeah?
Are those output values always going to be in order? Or could, like...
Oh, no, whatever.
Yeah. Because,
yeah. Now, there is no particular order. Each one of these curves is a level set. And you can write them down in whatever order you like.
So, like, you could have, for example, like, let's say, like, a line with, like, a 1, then, like, a negative 1, and then, like, a 2. Or would you, like, be moving backwards, or...
There is no prescription of which level sets you must look at or in what order you have to look at them. Yeah, each one is a tool that gives you some information about what the function looks like that you're looking at.
Okay.
Yeah. So it's free reign for the user. Yeah. Right. Yes.
How would you draw a level set if it's like going from R3 or to R2? Like, or to R.
Yeah, I'm going to lean on a point that I have written down here. Most of the time, we're going to be looking at real valued functions here. So it's not that you can't do it when you have vector value, but it's weirder and it's a lot less useful. So I'm going to kind of punt on that question. It's just not what we need to focus on. If you're curious, come talk to me in office hours. I'll be happy to. Yeah. Okay, so here's an example. By the way, this is a hopefully familiar example, somewhat anyway. This is called a contour map. And some of y'all may have seen contour maps before if you've ever gone hiking up in the mountains or something. And this is a way to kind of help people see what a three-dimensional mountain looks like, but with a two-dimensional picture. And the idea is, they'll draw one line here to represent, maybe 100 feet above sea level, and then maybe this next line is 200 feet above sea level, and then let's see, the next line maybe 300 feet above sea level, and then the next line 400 feet above sea level. You get the idea, right? So that's like I say, a pretty simple idea, really. It's actually these are level sets, right? But these are level sets of what I like to call the altitude function, right? Given any point in R2, given any x and y, given any latitude and longitude, as we normally think about points on the surface of the Earth, given any latitude and longitude, there is a corresponding altitude. And each one of these lines represents what I get when I set altitude equal to a constant. Let's see here. Let me finish my, so remember we represent the target like so. And for any given altitude, these are the points near that mountain that are at that altitude. And then you can say at a slightly higher altitude, these are the points near the mountain that are at that slightly higher altitude. And you kind of get a vibe of what this mountain looks like, sort of, kind of. It's not perfect. If I could carry around a three-dimensional model of the mountain, I guess that would be a better visualization, but it doesn't fold up in my pocket as well. And so, people tend to go with contour maps. Yes?
So would you only use level sets for discrete values, or would you ever do
No, that's a great question. I mean, the problem is that your picture would get useless eventually, right? So if I were to say, let's look at all possible altitudes, well, then I would have a picture that's entirely black, right? Now, what you can also do, a related thing, is you do what's called a heat map, right? And so the colors continuously vary, like in a spectrum. And then, you draw with the corresponding, and you would see kind of something vaguely like this, but in a sort of a continuous manner. And there's bazillions of heat maps all over the internet, of course, right? So that's another thing you can do. The problem there is now your ability to interpret it is contingent on your ability to precisely interpret color at a single right? And most people aren't very good at that. I'm certainly not. Okay, just for fun, I'll point out here is a real contour map. This is from Colorado, and when I was about y'all's age, I actually climbed this mountain, so that's why I picked it, right? So there's some nice things to see about this. You see the contour lines everywhere, right? But one thing that is confusing about this kind of picture is it's kind of hard to tell, wait a minute, which lines are at higher altitudes and which ones are at lower altitudes, right? That's intrinsic to the picture. And so they have these little helpful things that they do, like here they've written 12,600 right there, and that's just an indication that, okay, well, this line right there represents 12,600 feet. Right? And likewise at a few places for other contour lines. Couple of points of interest. Notice the zigzagginess, especially along in here. Zigzagginess of the trail. This little dotted line is the trail, right? Why do they do all this zigzags? And it's because, well, it's really steep. And you really don't want to go straight up the mountainside unless you're, way, way better shape than I ever was, right? And so the zigzag really helps, and for what it's worth, even with the zigzag, this is still pretty steep, right? This is tough going. Again, just, for me. Anyway, that's so you can see the motivation for this. The zigzags are basically avoiding cutting directly perpendicular to the contour lines, which would be straight uphill. Okay. You can also see on this map, roughly speaking, how steep things are. So, for example, along in there, right, look in here. Well, between each one of these contour lines, by the way, each of the small contour lines is 40 feet. I don't know where they came up with that, but whatever. And you get to cover that 40 feet of altitude gain over a pretty substantial distance there. So this isn't as steep. Whereas by contrast, check this one out, right there. Just from there to there, let's see, that looks like that's, oh gosh, it's hard to see. 1, 2, 3, 4. That looks like it's about 1,000 feet. There's 1,000 feet of drop right there. And it's really steep, right? It's basically a you wouldn't, if you fell, you wouldn't stop until, I mean, you'd hit that glacier going pretty fast, and then you'd slide. Extremely steep, very scary. So anyway, again, you can see that from the contour map, right? Because of the way the lines are drawn. So it's a pretty useful way to visualize altitude, and therefore a pretty useful way to visualize functions of two variables. Okay. All right. Moving along. Reminder for a given function. We've talked about two different ways to draw pictures of that function. Let's stick to two variables here, by the way, just to so we can draw some pictures. We have the graph construction. The graph construction, again, reminder, that's where you set the output values equal to z. We have the level set construction that we just talked about, which is, reminder, where you set the output values equal to some constant. So note the difference, right? These are completely different constructions. And I emphasize, we've done the one on the left a bazillion times, so much that we almost feel like we have to. We don't. This is a good choice, a beneficial choice in certain ways in certain circumstances, but it is an arbitrary choice, right? And check out our alternative here. We are not setting the value of the function here equal to a new variable. We're setting it equal to a constant. Gives us a totally different picture. The graph, you can see right here, there's now 3 variables in the equation. This gives us a 3-dimensional picture of a 2-dimensional surface, as we previously discussed. Level curves, still only 2 variables. In some sense, as it should be. Right? It's a function of 2 variables. So this is a picture in R2, and each one of these is a curve. So don't conflate them. They're totally different. They're geometrically different. By the way, we will eventually be talking about the calculus of graphs. How do I interpret what calculus looks like on graphs? It's a very, very different set of questions than how does calculus look on pictures of level curves. So make sure to distinguish. These are not the same thing. That said, if you were to take a horizontal cross section, keep in mind what a horizontal cross section is. A horizontal cross section is a horizontal plane like this. That means z is a constant value, so very easy equation. Z equals constant, right? And, well, notice a horizontal cross section of the graph. If f is equal to z and z is equal to c, then effectively we have f equals c, namely a level curve. So there's a really nice punchline in this little innocent observation, and that is, you can just read it straight off of the algebra. A horizontal cross-section of a graph gives you a level curve. And here's a picture of that in action. Here is a multivariable function of 2 variables. Right? Level sets. What you get when you set the function equal to constant. Level sets are these various curves. The graph. What you get when you set the function equal to a new variable. That gives us, again, this is a function. This is an equation involving 3 variables, and we're going to see what this equation looks like really soon. Possibly oh gosh, time always flies. Probably tomorrow. But I'm going to claim for the moment that it looks like this. It's kind of a bowl. Yeah. Take my word for it for the moment. And now here, let's draw the horizontal cross sections, z equals c. couple of horizontal cross sections there. And now notice, as predicted, those horizontal cross sections look just like the level sets. Everybody happy? Okay. Yeah, so be careful with all this stuff. I've already kind of given you the pitch of why we have to be careful on this is because the calculus of graphs is just very, very different from the calculus of level sets because they're totally different constructions. And so saying that differently, when you're looking at a curve, let's say, right, such as this line here, nice easy line, by the way. Let me point out this equation right here. Boom, it's just a line. Easy to draw the picture, old news, Algebra 1. If you want to apply the calculus of graphs to this picture, you have to figure out, well, what is it a graph of? If you want to apply the calculus of level sets to this picture, well, you have to know, what is it a level set of? And they're different functions, really different functions, right? So if you're not pretty uptight and precise about the difference between graphs and level sets and careful in how you do the algebra and how you sort of set things up, you'll get some wildly nonsensical answers. Right? So let's talk about how this works. I claim that this picture is the graph of this function. Notice it does not immediately leap out at you from the equation that we were given. So how do I know that we're looking at the graph of that function? And the reason I know is because I can write down literally what is the graph. The graph is what you get when you set your function equal to a new variable. So I'm setting it equal to y. Notice again that is exactly what graphs are. So this is the graph. And then notice, algebraically, these two equations are equivalent. It's a little trivial, a little bit of algebra to get from this equation to that equation and vice versa. So any point that satisfies this one satisfies that one. They are equivalent equations. I mean, we could quibble and say they're technically not exactly the same equation because, look, they look different, right? So I'm not saying they're the same, but they are equivalent in that each implies the other. Okay. So if you want to apply the calculus of graphs to learn something about this curve, this is the function you do it to. And don't make the mistake of trying to apply the calculus of graphs to this formula right here. This formula right here is not the function whose graph is this. So the calculus of graphs has got nothing to do with that blue formula right there. Okay, now all right, let's talk about level sets. We're going to learn fairly soon some calculus of level sets. Well, this line is a level set of this function. I know it is because I can write down exactly what a level set is. A level set is what you get when you set your function equal to a constant. In this case, I'm going to let that constant be 6. And check it out, then, this being exactly what a level set is, right? We set the value of the function equal to a constant. And sure enough, now I have an equation that is, again, equivalent to the original line. This time it's actually the same equation, whatever. The point is they're equivalent. So, so you can apply the calculus of level sets that we're going to learn really soon. The calculus of level sets you apply to this function in light blue. And if you apply the calculus of level sets to this function up here in green, you get garbage. It doesn't make any sense, and you get, your answer is going to be preposterously wrong. Okay. Last observation I'm going to make is you can also parameterize the line. So in fact, we actually have 3 different functions that in their different ways, let's see, let me clean up here just for simplicity. We have here 3 different functions that in their different ways describe this line. And by the way, there's going to be a calculus of parametric curves as well. So again, be make sure that when you start to apply calculus ideas, that you apply those calculus ideas to the right function. And the only way to get the right function is to, again, be precise and careful and kind of uptight about exactly how these things are defined. Okay, good place to draw the line. We see y'all on Friday. Okay, have a good one.